So thank you very much for the invitation, and Happy New Year to all. So I'm Oscar Gravier. I'm a third-year PhD student, and I'm working with Benoît Vermersch, Thomas Herald, Tristan Meunier, and Valentin Savin. And today I'm going to speak about low-distance surface code emulation for silicon-based spin qubit. So to start, I will give some context. As you know, we want to work with a large-scale quantum computer, and this computer require a very low error rate, down to 10 to the power minus 15, and this is beyond the reach of physical qubits. So to do large-scale quantum computation, we need fault-tolerant quantum computing, and these have two parts: quantum error correction to produce high-fidelity logical qubits, and also fault-tolerant logical operation. And in this talk, I will focus myself on quantum error correction. So in my point of view, it has started with a lot of theoretical work, and in '96, there were some proposition for stabilize the code. Then some topological code came, and then with Storic and surface code, there were some very big results with Kitaev and Fowler. And so at this point, a lot of experimentalists were interested to implement quantum error correction to their experimental setup. So for the trap ion, there were some good results with a color code of 10 qubits in 21. In 24, it was for a Rydberg atom to manage to do a steam code of 10 qubits and a carbon code of 16 qubits. And finally, there was three very good papers of Google from 21, 23, and 24 with a surface code of increasing the instance from 3 to 5, and for the last paper, 7. And for the last one, they managed to have logical qubits with better performances than physical one. Then, for the spin qubits, my domain, they were a good paper in 22, but with a 3-qubit phase flip code, so a low number of qubits. And even with a lot of great advancements with gate fidelity at the surface code threshold, they didn't manage to continue and to go to surface code for now, because implementing 2D lattice on such technology is very difficult. But silicon-based spin qubits have a big advantage. They are CMOS compatible, which means that we can take advantage of 20 years of silicon industry, and so there is a big scaling advantage. So the work have continued for surface code with theoretical work, and in 2024, there were two papers, one using polynoise model to adapt the surface code to spin qubits, and another one doing quasi-static phase damping error model based on spin qubits properties. And today, I'm going to present you the evaluation we have done with a state vector simulation, so a very precise simulation on surface code. And to answer the following question, we have done a realistic hardware error model. We have implementing an autocorrelated noise with 1/f power spectral density. And we have tried to understand the impact of a sparse architecture on surface code. And so today I'm going to answer these two questions. First one, how can 1/f noise be advantageous for surface code? And finally, how spatial correlation and shuttling in a sparse architecture affect the logical qubits. I will present this with the following outline. So first, I will present the hardware error model. Then I will briefly speak about the surface code I'm considering. I will finally give some metrics and then the numerical result of my work. For the hardware error model, so as you know, we want to map a surface code on a lattice of spin qubits. So to do such a simulation, we have to take big hypotheses. So for example, we are taking the hypothesis that we are able to do a 2D lattice of spin qubits, which remains very difficult actually, with a connectivity of 4 between qubits. We assume that we are able to do individual manipulation of qubits, and that each qubit can be followed by a dedicated reference in order to annihilate from his Lamar frequency in time. Then if we zoom a little bit on a 2-qubit system, we can see the hardware component. And for single qubit gates, we have the control gates, which will enable us to shift the energy of the qubits and apply some phase gate, like the Z gate, and some metal wire to do ESR, in my case, and to send a driving field to the qubits in order to compute X and Y gate. Then we can use exchange gates to shape the barrier potential between both qubits and control the G-coupling between qubits. As noise, we are considering the fluctuation of the electrostatic environment of qubits due to a two-level system that are switching in the device. And those two-level systems are switching with different frequency. And so it's creating a 1/f charge noise, which is well known here in spin qubit and in Grenoble. These fluctuations are going to impact the two manipulation parameters that are the Larmor frequency and the G-coupling. For the Larmor frequency fluctuation, we can see that there is a linear dependencies between the electrostatic environment fluctuation and the value of the deviation to the Larmor frequency. So in my simulation, I will directly use a 1/f signal to simulate each evolution of Larmor frequency of my qubits. And then for the G-coupling fluctuation, there is a double impact. First, there is the increase of the barrier, but there is also an impact on the distance of both qubits. So this double impact brings us with an exponential dependencies, and we will use such exponential function based on the value of the G-coupling to calculate the resulting deviation to the ideal value of the G-coupling. Now that we have the manipulation parameter and the noise in our system, I've done some simulation of native gates, which are gates that will be used here in our hardware model. And so to simulate single qubits and 2-qubit gates, we use Hamiltonian simulation. And here in red, you can see the noisy parameter I've been using. After doing some simulation with different pulse shape and thinking about implementing dynamical decoupling into a 2-qubit gate, we've been able to fool and to create single qubit and 2-qubit library with each noisy gate defined by their noisy parameter. And this enables us to do noisy circuit construction. So this is an example of a 2-qubit circuit with 1 qubit here in blue and the other one in yellow. As you can see, in blue and yellow, there is the Larmor frequency evolution in time, and so the noise, which is 1/f noise. And here in red, you have the G-coupling fluctuation over time with an applied exponential function on it. So at each time step of your quantum circuit, we make the hypothesis that the noise is static during the gate of the time. So we just have to look at the value of the deviation to the ideal one, and we can access to the single qubit library, have the noisy gate representation, and we replace each gate by their noisy unitary matrix. Then, when the circuit is full, we can do state vector emulation. And to do so, we use Captiva, which is a supercalculator, which helps us parallelize the calculation and speed up the process. And we do Monte Carlo simulation. So now I've explained how we can simulate a noisy circuit based on a hardware model of spin qubits. And I can switch to the second part, which is the surface code, which I will be working with. So in this work, so in this talk, I will speak about the surface 17 rotated code, which is a distance 3 code. Why? Because it has a very low number of qubits, and as I'm doing state vector simulation, it's becoming way too complicated to do simulation with a higher distance. in this code, you have two stabilizers, X stabilizer enabling to detect phase flip, and Z stabilizer for bit flip. And both have a dedicated quantum circuit. But as you know, we want to map it to a dedicated hardware, so we use conversion rules. So Adamer will be converted into a K gate, which is a native gate, and CNOT gate to a P gate. And thanks to these conversion rules, we can obtain the native gate syndrome extraction circuit, which will be representing in the following with this symbol. And then this syndrome extraction circuit takes place on a correction cycle. So here we will extract repetitively. Our syndrome extraction in order to create windows of Swiss syndrome. At the end of windows of Swiss syndrome, we will use minimum weight perfect matching to decode our windows and to obtain the correction to be applied. After each correction detection, we will correct the logical qubits and calculate the fidelity to the initial state. So, for example, to the initial state. So in this manner, thanks to the decoding and the calcul of the fidelity to the initial state, we can really follow the decoherence of the qubits in time, and that will help us creating the metrics that I will present in the following slide. Now for the metrics. So in this work, we have choose to work with a time-based comparison because it enables us to have a better, more closer to realistic, more closer to the reality of the dephasing, and so we can understand how is it dephasing by looking at the coherence time. So for the physical qubit, as you may know, we have two times, T1 and T2 star, and as T2 star is way smaller than T1, we will focus on this value. And to obtain this value, we will use a Ramsey experiment, which gives us a Gaussian decay that we can fit with such function. We also have to do the same thing for a 2-qubit system, and to obtain such time, we are using Ramsey experiments on a 2-spin qubit system, which is undergoing only noise due to G-coupling fluctuation. So we annihilate the Larmor frequency fluctuation for this numerical experiment, and we only focus on G-coupling fluctuation. And this enables us to have also a Gaussian decay which can be fit with this function, giving the value of the TG star. Then, if we want to do the same for a logical qubit, we can just look at the fidelity over time. And in that case, we don't have Gaussian decay, but we have an exponential one. So we do a Ramsey-like experiment. We see this exponential decay, and we can fit it with this function. We obtain 2 times T2L star for a plus logical state being stabilized, and T1N for a 0 logical state being stabilized. But as we are with a noise with Z biased, the T2 star L is smaller than T1L, so I will focus for the rest of my presentation on this time. So now that the metrics have been exposed, I can switch to the logical qubit performances. So here, I'm plotting the logical qubit coherence time as a function of the physical qubit coherence time for different value of TG star, which will be fixed. The first thing that we can see is, okay, there is a saturation of the performances of the quantum of the logical qubit, and this can be explained by the fact that because we have a noise in G fixed, as T2 star is growing, the fidelity of 2-qubit gate is limited, and so it's becoming the biggest source of error in our system, and so it's limiting the performances of our logical qubit. But the biggest information that we have here is that here with no exchange energy noise, we have a quartic dependencies, which is very good because that was not what we were expecting at first, as Fowler says that we should see for error rates quadratic performances. So these quartic dependencies is also see if we do a joint evolution of TG star and T2 star. Here I'm putting the same information but with a different ratio, but for different ratio of TG star and T2 star. Those ratios can be can change depending on the hardware choice that we are doing. For example, in my case, I'm doing ESR, but the ratio can change if we try to do manipulation with micromagnets in order to produce the driving field. So these quartic dependencies still, even if we have a joint evolution with TG star and T2 star. And how can we understand these quartic dependencies? So it's based on the fact that the logical qubits, that the logical error are converted towards the stochastic logical poly errors, which means that here we have Gaussian decay for the physical qubit, but as soon as we are co-correcting and extracting syndrome, we reproject our logical qubits to some poly errors, and so we don't have here a poly, but an exponential decay. And this is very good for spin qubit because, for example, in superconductors, we can't see such advantage because both physical qubits and logical qubits have an exponential decay. Then I can switch to the impact of spatially correlated noise. So as I've said earlier, the noise came from a two-level system distributed into the structure. And as these two-level systems are shared, it brings spatial noise correlation, which has been shown by these two very good papers from Yoneda and Rojas. And in the QEC domain, a lot of papers have studied some different noise model of correlation. And a lot of those papers have came with the idea that they shown a very strong negative impact on quantum error correction. So we wanted to try with this correlation model what is the impact on such simulation and correction. So as a starting point, we have taken the uncorrelated noise, which was in the previous result, and we had a fully spatially correlated noise, which means that this time we don't have one single signal for each Larmor frequency of qubits and each pair of 2 qubits, but we have just one single 1/f signal for all Larmor frequency qubits, and which will be used for all the G coupling value. And doing so, we had the first result. So first, it doesn't change the exponential decay, and we still have an exponential decay. Then, if we look at T2 star in function of T2L star in function of T2 star, we still have a quasi-quartic dependencies. So the impact is not that big and is not the same case as other paper. And if we look closer to the ratio, we see that it diverges, but it diverges with a sublinear divergence. So it diverges very slowly, and it's not impacting that big Hall correction. It was a very good result, but we are now trying to annihilate this impact and to understand it better with a toy model on repetition code and with white noise. And I can finally go to my last part, which is qubit displacement for sparse architecture. So why do we want to go to sparse architecture? And the reason is because we want to add readout qubits in order to be able to read the ancilla at the end of the syndrome instruction. And we also want to simplify the wiring, because increasing the number of qubits will create a big problem of wiring, and if you have a less dense structure, it's making it more easy. A lot of propositions have been done, and for example, there was the spider web array and the spin bus architecture in 22 and 24. And in our case, in our work, we are considering a structure like this with cluster. Cluster for manipulation, when we have a dedicated wiring for implementing single qubits and 2-qubit gates. And cluster for readout to implement a spin-to-charge conversion and then charge readout. So the ancilla have to shuttle from cluster to cluster in order to compute 2-qubit gates and to do the Sandrom instruction. At first approximation, and for those results, we are considering a shuttling that is modeled by another time with an alpha factor applied to the coherence time of the shuttle qubits, a shuttle time of 10 nanoseconds, and the results we had shown that we are able to do a quantitative, to have quantitative information on the impact of the shuttling. Yeah, just so here I'm plotting the logical qubit coherence time in function of the shuttling time or the number of quantum dots that the qubit have to cross for a fixed T2 star and a fixed TG star. So here I'm looking at the impact of the displacement over the addition of quantum dots to be crossed. And so, so we were happy to have some quantitative information. It's staying it's requiring a big displacement to be at the same level of the T2 star of physical qubits. And for alpha of 1, we were happy to see that there is dependencies of the logical qubit coherence time with this law. And we will be working on it a lot more to understand it and to add some less approximation on shuttling. And so finally, I can conclude. So by constructing this hardware model for spin qubit and by doing a detailed simulation on surface 17 code, we've been able to define some interesting metrics in order to have the full overview of noise impact on surface code. And so we have been able to show that there is an advantage on spin qubit using working with 1/f noise. That the spatial correlation have a low impact on logical qubits, and we've been able to quantify the shuttling impact. And as perspective, we are going to work to a larger distance code with Benoît Vermersch and Nathan Miscopin from Kobli. And so we will use tensor network to simulate up to distance 9. And we will use also polytrolling approximation to go beyond distance 9. We will also try to evaluate the approximation of polytrolling approximation by looking at same distance with tensor network and state vector simulation and polytrolling approximation. And with that, I thank you very much for your attention, and I will be pleased to answer your question.
Thank you for your talk. So, questions, okay?
Okay, so maybe I start. I have two questions, mostly yes/no questions. For the decoder, you have a sliding parameter, which is fixed to 3 here. It can be anything. You just take 3 because you want to, but it can be anything, right?
Yeah, it could be anything, but as we are working with a distance-free code, windows of Swiss Sandrom, it's the best you can have. And increasing this window, it might enable some little adjustment, but it's still the best thing.
Okay. And second question was about the quartic on slide 20.
Yeah.
The quartic scaling. This is for distance 3, and so if you implement a distance 5, you might expect something even better in terms of scaling, or not really.
Yeah. So as you increase the distance, so for the logical error rates, you will have 2 plus 1 over 2. So you will just add it a 2 to this number.
But that's not the logical error rate. That's coherence.
So this is the logical qubit coherence time.
Yeah.
If we look at the logical error rates, we will still have quadratic dependencies. And it's only when you look at the logical coherence time that you catch this difference with Gaussian and exponential decay, and that you bring the quartic dependencies. So this is not for the logical error rate, but for the logical coherence time.
Yeah, but my question is, if you increase code distance, is the scaling here, which is quartic, increasing also? You might have x to the power of 6 or whatever.
Exactly. Yeah.
Okay.
So it will increase by adding a square to your d plus 1 over 2. Exactly. If you want, I can. So, for example, here, the only thing that brings these dependencies is that our coherence time for logical qubits is proportional to this value, and for the physical qubit is proportional to this value. And then in the distance tree, we have this, but if you increase the distance, you will go to 4 and etc. You're welcome.
Hello, thanks a lot for the talk. So when you want to compute logical error rate, people usually use STEAM, but you seem to have redeveloped an entire state vector simulation. So STEAM is shot-based simulation. So why is that? Why can't you use just STEAM and fine-tune the error model to your case?
Yeah. So if we want, so if I'm not saying, if I'm saying right, if you want to use STEAM, you use a poly-noise error model. So if you want to use a poly-noise error model, you have to do a PTA in my case, and this polytrolling approximation can bring error. But you would also, but in my case, I'll need also to follow the qubits with an autocorrelated noise. And so to have this autocorrelation working and to follow the decoherence of the logical qubits, I cannot do that with STEAM. Yeah.
Another short question? Okay. Or it's, okay.
Yes, thanks a lot. I just wonder, when you consider spatial correlation between different noises, do you also consider correlation between exchange noise and single qubit noise, or?
Yeah, exactly. So in the case of fully spatially correlated, we are using one single time trace to represent the evolution of all the Larmor frequency of the qubits. And when we want to have the evolution of the decoupling noise, we apply a coefficient to obtain the right intensity, but we use the same autocorrelation. So they will all move together, to have like a fully thing, like the worst noise that we can think of.